So in the previous one, we had a special scenario before we made the equivalence point that was halfway to the equivalence point. At that point, the pH equals pKa. Any other time you are before the equivalence point but after the start, you are going to have to use the Henderson-Hasselbalch equation. And so we do the same thing as we did before. We find out that the number of moles of acid we're starting with, which we wouldn't have to do this calculation again because we did it before, but I'm just going to go ahead and rewrite it. So we're starting with 0.006 moles of our acid, HA. And we take the volume of our base that we're adding, converted to liters, times its concentration. And what we get is 0.005 moles of base O minus. And we're going to plug this into Henderson-Hasselbalch. Remember, we don't have to convert the moles to concentration because we're going to divide by the same volume because they're in the same flask. And in the end, that value is going to cancel out. So we just have to do pH equals pKa, which we found before in the previous one, where we take the negative log of our Ka, which is 4.01, plus the log of A minus over HA. Now, the way you find this is, again, if you write out the equation, you can do what we did before, where we have our HA plus OH minus gives us H2O and A minus. If I start with 0.006 and 0.005, my limiting reagent is the OH minus because everything's a 1-to-1 ratio. I just subtract that from both sides, or not both sides, from the left side and add it to the right. So I'll end up with 0.001 HA, no OH minus, and 0.005 A minus. Again, after a while, you can see the shortcut where the amount of OH minus you add is the A minus, and you subtract that from HA. And so what we get is A minus is 0.005 and the bottom 0.01. So all you would do is in your calculator, you would put in the pKa, which is 4.01, and then we are going to add the log of 0.005 over 0.001, which is the same as 5. And what we get is 4.71, which makes sense because we're adding more base than halfway to the equivalence point, so our pH should be greater than our pKa. If we are before halfway to the equivalence point, our pH would be less than the pKa. When we get to the equivalence point, because we're adding a strong base to a weak acid, our solution should be basic. And in the next example, we should have a pH that is greater than 7. So anyway, anytime you are between the starting point and halfway to the equivalence point, or starting point and the equivalence point, my apologies, you would need to use the Henderson-Hasselbalch. But there's a special scenario where if you're halfway to the equivalence point, you can just know that pH equals pKa. But you could still use the Henderson-Hasselbalch to figure that out because for that scenario, the log of 1 is 0. The next example, we are going to move on to where we reach the equivalence point, and we have to go from Ka to Kb.